Welcome to the lecture 28 of Physics 10 in 30 lectures. We start chapter 14, the last chapter of the textbook, with this lecture. We will start with chapter 14 overview, touching on all the topics covered by this long chapter, most of which will be addressed by the remaining lectures in this semester. This lecture set will focus on radioactivity and nuclear fission. Discovery and types of radioactivity is a borrowed Physics 4C lecture in which we tell a little story of discovery of radioactivity and how Rutherford classified them. Radiation safety lecture explains the ALARA principle and the distinction between ionizing and non-ionizing radiation. Isotopes and nuclear reactions wraps up the earlier radioactivity lecture with descriptions of alpha and beta decays, setting up the distinction between nuclear decays, a kind of spontaneous process, and fission chain reaction, a kind of stimulated process for which a device needs to be built. Fission chain reaction lecture illustrates the necessary elements of a fission device with the help of a PhET simulation. In the next lecture set, we'll look at the remainder of nuclear and particle physics topics we will cover this week. Now, here's chapter 14 overview. Hi, this is the overview video for Chapter 14, Nuclear and Particle Physics. Now, it's a long chapter, and maybe because it's a long chapter, this mind map as generated by Notebook LM didn't cover the entire chapter. It goes through section 14.9 nuclear fusion. So I'll bring up the second mind map when we get to that point. Now the good news is a lot of what's in this long chapter is optional. You only have a short problem set, 10 questions, 2 number questions. So for this overview, I'll just talk through what you will see in the lecture videos, a lot of it using borrowed Physics 4C lectures, and which topics you don't really have to worry about because you won't even see it in homework. So let's start out with the nuclear radioactivity that's covered in section 14.2, and that's pretty important for a lot of reasons. For some of you applying to radiology programs, this is frankly why they make you take this physics class. So in radioactivity, there are radiation types, alpha, beta, gamma. I lecture on that. So other than showing you this, I'll move on. The properties have to do with how easily they are shielded, their penetrating power, and I guess things that relate to what kind of particle they are. So ionizing energy, penetration range, charge and speed. Gamma rays move at the speed of light. Beta rays can move pretty close to the speed of light for high energy. Alpha rays are basically non-relativistic. Radiation detection and detectors, that's covered in section 14.3. I don't think you have any homework questions on this. So if you're interested, you can read. But I don't really lecture on it, and this is optional. Substructure of nucleus. This might be something that some people know from your basic background science knowledge, especially things about protons and neutrons. Now, if you don't, then that's the reason this chapter exists. And I also lecture on it, both what nucleons are, atomic number, mass number, isotopes, strong and weak nuclear forces. I think I put that off quite a bit to lecture 30. So if you want, read about it in this section 14.4. And magic numbers, I think that's in reference to the combination of neutrons and protons needed for stable arrangement. I do make a reference to it in the lecture. Now, I don't think you need that for homework. Okay, let's move on. Nuclear decay and conservation laws, section 14.5. I do lecture on this a bit, talking about alpha and beta decays as a form of nuclear decay. I don't really talk about decay series. And in the context of nuclear decay, conservation laws that matter will be conservation of like the electric charge. Linear and angular momentum, a lot of times you don't worry so much. I mean, it's conserved. Angular momentum, I will mention that when we are introducing neutrinos. And mass energy, this is the famous E equals mc squared. You take the differences in rest mass, rest energy of the particles involved in the reaction, and that gives you how much energy is released. Nucleon number, that's one of the conserved quantities. I think I talk about conservation of baryon number. And electron family number or lepton number is also conserved within each family. Electron, muon, and tau lepton. So all of that is lectured on, and the things you need for homework, you'll see them in lecture. Half-life and activity, that's covered in section 14.6. Decay constant, guess both the decay constant and exponential decay, we focus on less complicated math, just handling half-life. You will see that in homework, and I do have a homework help video in lecture 29 that will walk you through the calculation. And these units, I don't think I even mentioned them. And radioactive dating, there's a homework example. All right, let's keep going. Application and effects. I think that's probably the same material that's covered in section 14.7 and 14.8. Yeah, medical imaging, that's section 14.7. Radiopharmaceuticals and so on. I think there's a homework question covering these, or maybe it's the essay question. If it's essay question, you will see them in lecture 30 as I do the overview of Unit 4 essay questions. And biological effects, that's sort of about the dangers of ionizing radiation. So I do talk about ionizing versus non-ionizing radiation, and I have a radiation safety lecture. I don't really go into these units of rads and gray and RAM and sievert, RB and quality factor, but I do mention DNA damage and some of the precautions you need to take with the alpha and beta sources. And I guess what I talk about can be summarized as ALARA principle, as low as reasonably possible, in reference to exposure to radiation and as a way to limit that exposure, time, distance, and shielding. You'll see that in lectures. Now, in the lectures, we'll cover nuclear fission before fusion, but since the nuclear fusion is here, also in section 14.9, let's look at that first. So when you look at nuclear fusion, there's kind of a chain of processes that'll fuse hydrogen into helium. And in that process, some of the protons turn into neutron and all that. So that's proton-proton cycle. And really the thermonuclear power is the only quote-unquote practical application of nuclear fusion, where we have used it in the context of nuclear weapons, covered in section 14.11, to ignite the fusion using a fission bomb, an A bomb. So when we say thermonuclear bomb or thermonuclear power, we are talking about a process that utilizes fusion process. And these magnetic confinement and inertial confinement approaches, these are ongoing research approaches in trying to induce a controlled fusion in a way that we produce more energy than we put in to ignite the fusion. So far, not quite successful in the sense that we don't get more energy out than the energy we put in. And the main challenge is in overcoming this Coulomb repulsion barrier. That's where thermonuclear bomb is a lot easier because you use the power of a fission bomb to meet the conditions needed for fusion. I talk about that in the lecture. Okay, so that's like a first 2/3 or so of the chapter 14. Let me go to the second mind map that I generated only using sections 14.10 through 14.14. Okay, I think this is the one. Nuclear and particle physics. Again, I would have liked to have a single mind map that covers entire chapter 14, but I guess it's too long of a chapter to do that. So, nuclear fission. This is covered in section 14.10. And I do talk about the fission chain reaction. There's a nice PhET simulation that illustrates that. So when we talk about fission, it's about splitting heavy nuclei, and at the really heavy end of the periodic table, splitting the nucleus releases energy. Iron is at that middle point. Isotopes that are heavier than iron, they release energy by undergoing fission or some sort of separation process. Elements that are lighter than iron can release energy through fusion. But we are usually talking about much heavier isotopes like uranium, plutonium when we are talking about fission. Now, when we are looking at fission reaction, either in a nuclear reactor or in a bomb, we are inducing this process through introduction of a neutron. And a key part is what we call chain reaction. And I have a nice PhET simulation that illustrates that. There's an important aspect of criticality, which goes to whether each reaction produces more neutron than was needed to get to that point. And this is an important consideration in operation of nuclear reactors and nuclear bomb and nuclear reactors. I don't think I go into as much detail of it. I don't think I talk about moderators and control rods. I do mention how uranium-235 and plutonium-239 is fissile. Uranium-238 is not. There's a simulation that illustrates that. Breeder reactors, I don't think I talk about that. So plutonium-239 is produced out of uranium-238, which on absorbing neutron becomes uranium-239, and then it undergoes a couple beta decays to become plutonium-239. I don't think I talk about that. Again, all of that optional. There isn't really a homework question, so you can read the section 14.10 and section 14.11, nuclear weapons, covers nuclear weapons. Thermonuclear power, I guess in the earlier mind map, that wasn't in reference to bombs, that was in reference, I don't know, the fusion process going on within the sun. So this is specifically about weapons, fission bombs. They need critical mass, and both of these types of bomb designs are bringing subcritical masses together as rapidly as possible, and that has like a built-in limit on how much explosive yield you can get. So that's where thermonuclear bomb comes in. A lot of research here was done during Cold War, kind of arms race between Soviet Union and US. And here the fusion fuel is triggered by a fission bomb. So this overcomes the inherent limitation of fission bomb, which can be only so big because the subcritical masses that you bring together, they have to be subcritical. But using that, you ignite fusion, then the fusion piece can give you much bigger yield. So I'll leave that there for nuclear weapons. I do talk about that in the lecture. Now, the remaining nodes here are covered in sections 14.12, the 4 basic forces, 14.13, particles, patterns, and conservation laws, and 14.14, GUTs, grand unified theories. And I will say those are all kind of optional, and some of the related lectures you will see them in lecture 30, which is next week. And a lot of this you don't need them for homework, and the bits you do need for homework I do lecture separately, kind of as a homework help thing. I just say all these things, take a look at the textbook, make a sense of what's in the lectures, and if you have any questions, please let me know. I would love to answer your questions about these 3 sections and things you are curious about. But all of this is, again, optional. You don't really need them for homework and all that. So I'll just leave that there. You've seen the nodes expanded, and you can read more in the textbook chapter if you are interested. So that's it for chapter 14. Again, this is a long chapter of which the required portion is really small. So you might want to maybe look at the homework questions so that you don't get overwhelmed as you look at this long chapter. So that's all. Thank you so much. This is the last chapter overview video. I will see you in the rest of the lecture videos and maybe in Physics 4A for those of you who are taking this class as a preparation for Physics 4A. Thank you. Bye. So last time we actually talked a little bit about X-rays, right? Do people know how X-ray was first discovered?
From the cathode rays?
Yeah, cathode rays. What are cathode rays? Electron. Okay, let me rephrase it. So let me discovery of X-rays. So there's a device called a cathode ray tube. How many here have heard of something called a CRT? That's how people used to make TVs. And those old TVs, this stands for cathode ray tube television or screen or whatever. So what a cathode ray tube is, you have a cathode in a vacuum tube. Anyone here know the distinction between cathode and anode? Yeah, which one is positive? Cathode is positive? I thought cathode was negative. Cathode is the one that emits electrons, so it's gotta be negative, right? Yeah.
Cation is. Yeah, sometimes it's confused.
Never mind. I know what a cathode is. I don't need to know what cation is. Okay, so cathode. So the cathode ray tube is, imagine a evacuated tube, and you have an electrode poking inside. And so this is physics, so this one I know. This electrode has to be negatively charged. So it's negatively charged by, you can do it with a battery by use of high voltage device or something. Let me label it as, so you hooked this up to some negative high voltage thing. So it's negatively charged. Then what people figured out is that there are some kind of particles that's emanating from this cathode. If you charge it negatively enough, then there are just particles that kind of come out of it. You can visualize these particles in many different ways. The way your old screen television does it is you have a glass here, and you coat it with some fluorescent material that when it's struck by one of these cathode rays, it'll glow green. That's the old monochromatic green screen that you may have seen. Or if you fill up this tube with a little bit of gas, like argon is common one, then you will see a green glow as these particles kind of move through the gas, exciting the gas. So you can kind of collimate the beam if you want, put some barriers here and here, and then this kind of geometrically limits where the beam can go. So with this collimation device, you would have a kind of cathode ray that goes like this. Okay? So this is this ray is what people would call cathode ray, and so cathode ray tube is that device. And I hesitated when Gauss said the cathode ray is electron. The subtle distinction is cathode ray is a beam of electrons. Right? So when people were initially studying these devices, they didn't know what cathode ray was. But so the discovery of electron is credited to J.J. Thomson. He's the one who kind of identified it as a distinct particle, separate from any other elements, any other atom. It's its own particle. He characterized its mass to charge ratio. You guys actually, well, for those of, I don't know if you guys do it at Laney and other campuses, but here we have a E over M experiment in physics 4B.
where you measure that charge to mass ratio of the electron, cathode ray. So what cathode ray is beam of electrons. So what you should imagine is this is really emitting these electrons. And you can make an arrangement so that maybe these two plates are charged. So you have a negative high voltage here hooked into positive high voltage here. So it's like a battery connected to both of them, except it's a super high voltage. It can be thousands of volts or tens of thousands of volts or even hundreds of thousands of volts. Then when an electron goes here, and if many of them will hit this target, but if it ends up going through, then the electron that's moving out here might have as much energy as, so if let's say that the voltage difference here, delta V, is about 100 kilovolts, 100,000 volts. Then after electron goes through this much potential difference, it'll have kinetic energy of about 100 kilo electron volts, right? Yeah. All this is actually, it's fairly doable. 100 kilovolt is not that high as far as high voltages go. People can put like megavolt on a, well, you can, 100 kilovolt, it's small enough, you can actually get that on that device. That Van de Graaff generator, if it's clean, free of any nicks and defects, then that can get 100,000 volts. So, so people were playing with this device. They were doing experiments with it. And this is what they discovered. Somebody, I'm going to say Röntgen, one of the German physicists, he discovered that if you put a photographic plate here, some kind of film, photographic plate, something that will be activated if light shines on it, that after a while, this would be exposed. I guess somehow he traced the source of the exposure back to cathode ray tube. And that probably happened through barriers, I'm assuming. So he started putting other things, like, let's say, a block of wood between the cathode ray tube and the photographic plate. And this photographic plate would still be exposed. So he attributed it to something that's coming from this plate. It's not the cathode ray, because the cathode ray is stopped by this plate at the end. So there's something else that's coming from here. Something else that's coming from here. And whatever it is, it's something that's able to pass through wood. It's able to pass through a lot of materials that visible light can't really. And it's a strange property. People thought it was strange, so this was named X-ray as a kind of, well, it's a strange ray. It seems to go through a lot of material. We don't really understand what it is. This is before development of quantum mechanics. This is like 1870s or 1880s, 90s. So it was called X-ray. But I guess to an extent, from an experimentalist view, this is fairly easy to understand. The moment you turn off this cathode ray device, this X-ray also turns off. So it's something that's coming from cathode ray tube. When you have these high energy cathode rays that are suddenly stopped, then it emits this X-ray. Now for us, with the perspective of quantum mechanics, we understand what all this is, right? Kinda. What kind of particle is X-ray? It's a photon, right? It's a high energy photon. So what's going on is that this electron with the energy of 100 kilo electron volts, let's say when it suddenly comes to a stop here, then it's emitting this, its energy is being lost as light. So this light, what this is a photon with energy of 100 kilo electron volts. That's really what that X-ray is. This high energy cathode ray or high energy electron is losing energy as it's suddenly coming to a stop, and that energy is being carried away by a high energy photon. Yeah? But it's exciting thing for people to study. And now the rest of what we are talking about with the nuclear physics actually has nothing to do with the X-ray. The reason I started the introduction with this is because it leads to a discovery of something called radioactivity. So discovery of radioactivity is what I really want you to talk about. And the reason people noticed the radioactivity was because people who are working on similar things as this discovered something that was emitting radiation that was similar to X-ray. But unlike X-ray, it wasn't coming from cathode ray tube. It didn't have a power source. You couldn't turn it off. It was just coming from some material. So that discovery is described in your textbook here. And I will just tell you the story briefly, maybe. I'll tell you the story. I'm not sure if it'll be brief. So Becquerel is the guy who discovered radioactivity. And I guess this is the sort of cartoon illustration, so you can read that too. Either works fine. Cartoon illustration would be, so the X-ray was discovered with exposure of photographic plates. And radioactivity was discovered in a similar way. Somebody, for some reason, stored photographic plates near some material. This guy, Becquerel, was studying uranium salts he was studying some fluorescence or something. And he happened to store these photographic plates near uranium salts. And this is kind of one of the weird things. It's kind of easy to imagine how this discovery wouldn't have been made. So he had the photographic plates stored here, near some material that he didn't know had a special property beyond the fluorescence. And for whatever reason, he decided to develop these unexposed plates. Who knows why he did that? But he decided to develop these plates. And when he did, he found out they were exposed. That's, I guess, when he tracked down, it was stored with uranium salts. So this uranium salt must be emitting some kind of ray that's X-ray-like. But it's obviously not an X-ray because we know how X-ray is produced. So whatever this is, it's a strange kind of radiation like X-ray, but it is not quite X-ray. But this is the beginning point of study of radioactivity. Because with the radioactivity, it's very specific to material property. So most of the things you see around you are not radioactive. I think we are legally required to stay that way. We are not. People used to work with radium, like painting clocks with radium, and like you Google search radium girls. There's some big lawsuit about how people running the company didn't properly inform their workers of the hazardous conditions they are working under. So radioactivity, it's material specific. So uranium is one element that has a lot of radioactive isotopes that we'll talk about. And so once this was discovered, then a lot of other people were looking for more radioactive elements or elements that have radioactive isotopes. I'll just throw out some names so that you know some people who've done a lot of work in radioactivity. One is a guy named Rutherford. Does that name sound familiar? Yeah, he's the one who did the Rutherford experiment. He used the alpha rays there. Those alpha rays come from radioactivity. So that would be americium, but I don't think americium was discovered then. The other person, there are many other names, but at least the two that I should give you is, the other person is Mary, I'm not gonna be able to spell her name right, Marie Curie. So she's one of the few people who have 2 Nobel Prizes. I think one in physics, one in chemistry, I think. And she discovered a lot of radioactive elements. One in particular is easy to remember. She discovered the polonium. And the reason it's easy to remember is because she's a a scientist working in France, I think, and she named it polonium after her home country, which was, I guess, I don't know, being ruled by Russians at the time. I don't know who would be ruling Poland back then. But so polonium is one of the radioactive, or one of the elements that have radioactive isotopes. And I guess we'll mention some of this. And when we get into these radioactive isotopes, one thing you will notice is that when you look at the periodic table of elements, a lot of these radioactive isotopes, they will be somewhere, they are all somewhere down here. They are at the high N value or high G value. So uranium is element right here, element number 92. Polonium is, where's polonium? Pu, right?
No, the oxygen, sulfur, yeah, 84.
Oh, 84, yeah, polonium. And americium is a common alpha source that's used in your smoke detectors. So a lot of these radioactive elements, they'll be found here. Cesium there are radioactive versions of cesium. So people started discovering, once they figured out this is something that happens, they started looking for other elements that have exhibit similar kind of behavior. And one of the main work that was done by Rutherford was he categorized the rays coming from the radioactive elements. It turns out these radioactive, or the rays from radioactivity, are more complex than X-ray. It has multiple components. So this is the place where the study of radioactivity enters. It's radioactivity, it emits ionizing radiation. And this strange feature that Becquerel noticed was only one component of radioactivity, but the other two components that wasn't part of this is also a type of ionizing radiation. And it's something to be careful with if you ever work with them. And your textbook chapter 10, section 4 lists all three types here. And this is a very handy graphic that kind of, in one picture, shows you the property of these three components that are emanating from radioactive elements. So let me just list them here. So the three types of ionizing radiation that come from radioactivity are alpha rays, beta rays, and gamma rays. And they all come from radioactivity. And in fact, as far as the definition is concerned, that's the real distinction between X-ray and gamma ray. I mean, there's a kind of typical energy range for X-rays and gamma rays. Typical energy range for X-rays, it goes from 1 keV to maybe 100 keV. And typical range for gamma ray, it usually ranges from around 1 mega electron volts and up. That's the typical energy range, but that's not what defines gamma ray. What defines gamma ray is that it's a high energy photon that comes from radioactivity. Oh wait, I kind of gave away the punchline. So when so these alpha, beta, and gamma rays, they were given these names for a reason. And this is the picture that kind of illustrates why they are categorized that way. It's people here know Greek letters, like you know A, B, C, right? When you learn Greek letters, these are the first three Greek letters: alpha, beta, gamma, and then delta. Yeah, I think. Anyways, alpha, beta, gamma. So scientists, physicists, these are a little bit more creative when they are naming particles. Back then, they weren't. So Rutherford was the guy who worked on these different classification of particles. And I guess he wasn't all that inventive, so he called them A, B, C, essentially, except in Greek. So the way he categorized them is by their penetrating power. You can see that in this picture here. Alpha ray is the least penetrating particle. So I guess I should give the typical energy ranges that people see. Alpha rays, so let me write down the kinetic energy. Kinetic energy of alpha rays range around MeV, 1 mega electron volt, or between 1 to 10. That's a typical energy range. And alpha rays are blocked by almost anything. In fact, air stops it. So if you have about this much air, as alpha rays go through the air, colliding with the air molecules, it would get stopped completely pretty quick. And in fact, now as it's stopping, it ionizes the air around it. And that's how the alpha rays in your smoke detector coming from americium is supposed to work. It ionizes the air around it, and that's affected by smoke particles. That's how your smoke detector works. So alpha rays, that's stopped by anything, it's stopped by paper, piece of paper. So this means alpha ray has a very distinct characteristic that's different from beta or gamma. In one sense, alpha rays are very safe, because if I have a very strong alpha source sitting here, I can kind of just stand far away and the alpha rays won't reach me. The air will stop it. In fact, do you guys remember, like in cartoons or whatever, when you see like radioactive rod, you see glowing in green hue, right? What that is it's all the alpha rays emanating from that. That's ionizing the air, making the air fluoresce. That's why they glow green. That radioactive green is coming from this. And it's it's easy to shield against. But the picture kind of flips around the moment the alpha ray source is on the wrong side. As long as it's outside my body, it's one of the safest thing to handle. We just don't, we just don't get too close to it, or if you have to handle it, you wear a glove. The moment it's inside my body, it's the most dangerous thing. Because when you look at beta or gamma rays, there's a good chance that gamma rays will just pass through my body without doing any damage. Alpha rays are guaranteed to react with something in my body and cause cancer somewhere, wherever it is. So one rule with the alpha ray sources, don't eat it, please. You think I'm joking. So that means,
It happened kind of recently, right? The Russian spy or something?
polonium poisoning? Yeah, that's how they died. So don't eat it, please. And if you are working with alpha ray source, what that amounts to is, most of the time you will be working with a sealed source, as in you won't be touching it directly. But if you do touch it directly for some reason, wash your hand. Treat it like you touched the lead. Because if you accidentally eat it, it's far more dangerous than any of these other two. So that's alpha ray. It has the least penetrating power. The one with the next level of penetrating power is beta ray. And I guess beta energies come in a lot of different range. The kinetic energy of beta ray, I think it comes from, I've seen numbers as low as 100 keV and as high as, I don't know, let's just say 1 MeV. So in terms of the energy, the beta ray isn't all that different from alpha, but the beta rays are more penetrating. They would definitely go through paper, and but they get easily stopped by pieces of metal. Like aluminum is often used in beta ray shields. Sometimes people just have a thick plastic as a beta ray shield. So it goes through materials better, but not as well as the next thing in the list, the gamma rays. And the gamma rays are the ones in the energy range of, well, I say kinetic energy, but it's all energy. Kinetic energy of around 1 MeV or higher. So it goes through almost everything. And we like to think of lead as blocking gamma rays, but the thing is, if you need a pretty thick lead to block gamma rays well. So I forget, it depends on the energy range. If we are dealing with 1 MeV, to reduce the amount of gamma rays by a factor of 10, I think you need a thickness of about 1 centimeter of lead, which is not which is not small. And if you have to reduce it by a factor of 1,000, then you need now inches of feet of lead instead of just a centimeter. So that's how these particles are characterized. And you can kind of maybe guess from these drawings, but I shouldn't play coy too much and just give you what these particles really are. Because back when they were studying this radioactivity, we are talking about early 1900s, late 1800s, they didn't know what these were. But today we know. Gamma ray, I think this is the one that you guys already know, so let me just spit it out. It's a high energy photon. So really, in characteristic, gamma ray is the same thing as X-ray. X-ray is a photon. Gamma ray is a photon. And at low energy limit of gamma ray, it will be indistinguishable from high energy limit of X-ray, because it's the same thing. And so when you think back to here, the component of radioactivity that was behaving like X-ray, that was the gamma ray. So that's it. So that's the component of radioactivity that penetrates through most material. Beta ray, depending on the source, may not have penetrated through desk material or whatever. Yeah.
What makes beta rays, just out of curiosity?
What makes beta rays?
Yeah, like would there be like a natural element you use, or can you produce it by using electricity and stuff?
So let me tell you what beta ray is.
Okay.
What beta rays are? They are electrons.
Because I know for work we use it. That's why for like non-destructive testing to like test the body of an airplane.
Yeah.
I know you shoot beta rays at it. You have to stand behind like a shield.
Uh-huh.
And then you can see if there's cracks developing in the actual frame without taking the skin apart.
I see. So if you're calling it beta rays, whatever device you're using must be based on some kind of radioactive element.
Yes, that's why I was wondering
Yeah.
what was in it.
Yeah. Now you could do the exact same thing with the cathode ray tube. The only difference is that if you're using this, you would need a power source. Whereas if you're using a radioactive element as your power source, then you don't need a separate power source. So there are some common elements used. I think tritium is a common one. There are some emergency lighting that's based on beta ray. As in, they have some tube with a fluorescent coating, and the tube has hydrogen gas in there with some fraction of tritium, which is hydrogen with the 2 neutrons stuck to it. It's radioactive. It decays by beta decay, and so, yeah. Does that answer your question? Yeah. So here's one thing I want to point out now. We have 3 different names for electron. There's electron, there's cathode ray, there's beta ray. So when you use these 3 different names, it depends on the context. And I will tell you, I have at least 3 different names. I have the name I go with you guys, Andrew. I have my Korean name that my family sometimes calls me. And I have another name that I use with the people who can't pronounce my Korean name. It depends on the context. When you see electron just by itself, not doing anything, then you call it electron. When it's in a tube, in a device like this, that's designed to shoot out the electrons with high energy, you call it cathode ray. When it's coming out of a result of radioactivity, like decay from some decaying element, you call it beta ray. So those are all the same names for one and the same thing, electrons. I guess one thing I should be careful with is sometimes what we call beta ray may not be an electron. It could be something called positron. It's a version of an electron that has a positive charge. So I think that's also called beta ray. We don't have a separate name for that for some reason. And alpha ray is the most complex one. And I guess I should give you the simplest description of alpha ray. What it is it's a helium-4 nucleus. Do people know what I'm talking about when I say helium-4? I don't think we've talked about isotopes yet. Have we talked about isotopes? Okay, we need to talk about isotopes. So when we talk about isotopes, this will all make sense. We'll just leave this here. This is actually, if you take a helium, commonly occurring helium, take away 2 electrons, then you get what's at the core of alpha ray. It's just that, so we call it alpha ray when it's coming out of a radioactive decay as a result of radioactive decay. Yeah, question?
So why is gamma a radiation and X-ray isn't radiation? Like why do we call gamma rays radiation?
Oh, they are both radiation. So I guess they're two similar sounding but different words. Radiation and radioactivity.
Oh, I see.
Radiation refers to anytime something is radiated, something transmits energy. In fact, this beta and alpha, they are not even electromagnetic waves. But these rays are emitting energy in some way, so we call it radiation. And the thing to be careful about is they are ionizing radiation. And your textbook actually goes into more detail of how these, how they were separated and how their properties were determined. And it's an interesting physics problem because this would be one way to do it. You have a radioactive source, which may be a source for all three different types. And you would distinguish them by, well, beta ray bends more, so it must be lighter. Alpha ray bends less, so it must be heavier. Gamma ray never bends, so it must be neutral, electrically neutral. And you start ruling out things, and at some point you look at the charge to mass ratio, and charge to mass ratio of beta ray happens to match charge to mass ratio of electron. So you guess there must be an electron. And charge to mass ratio of alpha ray somehow is, I guess, small enough to match that of a helium atom. Or helium atom if it lost to 2 electrons. So that's how people guessed that alpha ray might be helium nucleus. And I don't know if your textbook covers it. There's a story of how Rutherford actually determined that it is actually helium atom. He kind of emitted the alpha rays into a vacuum chamber, and then vacuum chamber that was all vacuumed out, and then later on he actually detected the helium that must have been produced from the alpha rays by recombination. Oh, all right.
So let me call this radiation safety, or as a subtitle, types of radiation. And what I'm trying to replicate here is actually, it's a training that I had to go through. In my previous research work, we had to use a radioactive source for a particular project I was working on. So we had to get approval for it. We have to get the source from a place at UC Berkeley that keeps them safe. I think the person was from LBL. Actually, the source we borrowed from LBL, but we had to go through UC Berkeley's EHS, environmental health and safety or something. So if your job requires you to work with radiation or radioactive source or any other radiation source, you would be required to go through similar type of safety. So the talk that I'm giving is not meant to replace that training, which is more comprehensive and you get tested on it. And but this is as a kind of a taste for people who might be going into those fields, medical fields, or people who might never get to those. This is kind of the thing that people in those areas would have to deal with. So I call this subtitle types of radiation, because that's the very first thing that you think about. When you think about types of radiation, the very first classification is actually into these two categories. One is what we call non-ionizing radiation, and the other is, I think it's kind of, it's maybe evident from the wording. It's like, there are two types of people. One type that can be put into categories and the other type that cannot be put into categories. So the other is ionizing radiation. So non-ionizing radiation, it can describe a lot of them. I think the biggest category of non-ionizing radiation is what you might call low energy, EM wave, electromagnetic wave. And frankly, a lot falls into this category. There's many of those words which are, so radio waves is one of them, microwave, Wi-Fi signal, which is technically microwave signal, infrared, visible radiation. Sometimes if you look at labels on laser pointers, you might see, oh, it produces a visible radiation, and like visible radiation is perfectly fine and safe as long as you don't shine it into your eye. And even when you do, it just hurts your eye and maybe damages it permanently, but not with laser pointers. Oh, and I guess cell phone signals like a 5G. These actually just fall under microwave. Microwave is a specification for a range of frequencies in the EM wave spectrum that I think you saw in chapter 12. And it's around the gigahertz range, and a lot of the wireless network signals these days are at that range. They don't necessarily operate at the same frequency as your microwave oven. So all these are non-ionizing radiation in the sense that all these have photons, particle of light with not enough energy. Not enough to do what? Not enough to ionize the atoms and molecules. Not enough energy to give to the electrons to liberate them from atoms and molecules. And with this non-ionizing radiation, the shortest thing I can say is that there has been no study that has ever shown any kind of health hazard that's associated with the non-ionizing radiation. The closest to would be microwave, through the same mechanism as how your microwave ovens work, can heat up your body to the degree that it causes burn. But you would feel it as a burn. So, I see the question, is there a cutoff for what's considered low power? So with the lasers, the kind of power that you are worried about is slightly different, because when I say photons with not enough energy, I literally mean photons in the quantum mechanical sense. You saw this expression, energy of photon is Planck's constant times the frequency. So with the laser pointers, with the, like there's a CO2 laser that's used for cutting stuff, so no matter how much energy you put into the laser, it will still not cause ionization. With some of those lasers, like CO2 lasers, the real danger is a mechanical danger, as in it can cut through your arm, for some of those. And the biggest hazard with the high-powered lasers is usually with your vision eye. That's why people working with high-powered lasers wear goggles. Some of them are designed to protect against the specific wavelengths that the lasers that they're working with operate in. And that's an entirely different safety talk. That's a laser safety talk. And I'll just say for a lot of the continuous wave lasers, the safety mechanism that we rely on the most is your blink mechanism. As in, if a bright light shines into your eye, we will naturally tend to blink, and that'll protect your eye most of the time. In the research settings, people work with pulsed lasers, where a very short pulse can deliver a large amount of energy in a short amount of time. In those cases, your blink response isn't quick enough to actually respond. So those are the circumstances where you have to be extremely careful, but those are also research settings where you wouldn't get access to those lasers unless you go through this training. So that's enough about non-ionizing radiation. That's a radiation that's totally safe to the extent we can tell. We don't worry about it. That's frankly not even about the topic of chapter 15. I want to address this because I think radiation is a loaded word, particularly in common popular usage. Sometimes people get scared whenever they hear the word radiation, and there's no reason to be, because it could be easily referring to non-ionizing radiation, and there's nothing to worry about. Ionizing radiation is the one where you need to take care and you need to respect it. And there are many types of ionizing radiation. One of them is kind of the exact contrast to this. So any high energy EM wave would be considered that. So what's considered high energy? And looking at this, high frequency would start out with UV rays at certain ranges. And above UV rays, it's X-rays that are ionizing radiation. They have a high enough energy. So that's one, but that's not the only one. All types of nuclear radiation is also ionizing radiation. So within the context of chapter 15, you have heard alpha rays and beta rays, and I already mentioned the gamma rays. Yeah, and there are other more less common types of ionizing radiation that you are really only exposed to in specific settings. Either you are out in the outer space or you are working with the particle accelerators. So there are other radiations. So if you're out in outer space or you're just high up, one source of radiation that people think about and make sure that they take into account are cosmic rays. And cosmic rays, what they fundamentally are is mostly high energy protons that have been accelerated to relativistic speeds by something somewhere. And neutron radiation is another one. But given that free neutron is unstable, it decays, and there aren't common processes that just produce neutron other than in like nuclear bombs. So neutron radiation is something that you might get exposed to if you're near nuclear reactors or research setting. But there are other sources of radiation that has potential to cause either ionization directly by imparting enough energy to electrons in atoms and molecules, or they might be producing secondary radiation that causes ionization. Neutron radiation is actually one example that can cause secondary radiation. If you're looking for a phrase to Google search, you can look up something called neutron activation. This is one of the rare circumstances where exposure to radiation actually causes something to be radioactive. With the alpha, beta, gamma, and X-rays and UV rays, exposure to those things don't cause things to become radioactive. But neutron radiation can cause things to become radioactive through the process called neutron activation. So that's types of radiation. And when we are talking about radiation safety, we are talking about if your work requires you to somehow become exposed to ionizing radiation, that's where you do the estimate, see if you are in a situation where you could potentially be at a higher risk of getting cancer or danger of death, then organizations are required to take necessary steps to make sure that people are safe. And I guess I don't have enough time to talk in detail about alpha rays, beta rays, and gamma rays, other than to refer to this diagram here. So this is a good nice illustration of those three very common nuclear radiation, alpha, beta, and gamma. And beta and gamma rays are more like each other than alpha rays as far as radiation safety is concerned. And it has to do with their penetrating power, which is actually how they are named. Rutherford was basically calling these ABC in Greek, in the order of penetrating power, from the least to most. Alpha ray has the least penetrating power, beta has the next, and gamma has the next. With the beta rays, the penetrating power of beta ray really depends on its energy. Low energy beta rays can easily get blocked by thin piece of metal like aluminum, like a few centimeters of aluminum can easily shield the beta rays. Or in biology research settings, I've seen people use plastic acrylic, like a thick layer of acrylic is enough to block beta rays of certain energies. There are beta rays with a much higher energy than usual. Those require most care to shield. That's where you would want to consult with the people who know what they're doing. Because with a very high energy beta rays, you worry about secondary radiation. As these high energy electrons slow down, they can release their own gamma rays. So if you try to block high energy beta rays with the lead shielding, sometimes that produces gamma rays that's not adequately blocked. So beta rays is potentially complicated. Gamma ray, in some sense, is very simple. It's an electromagnetic radiation. And it's like X-ray, so it goes through paper, goes through most metal that's thin and light in atomic weight, like aluminum, goes through concrete quite easily. Really, to reliably block gamma rays of varying levels of energy, what you need is a thick lead shielding. High G, high atomic number material. Lead is the most common one because it's easy to work with and only slightly toxic, only if you eat it. And even then, I think for every centimeter of lead shielding, gamma ray gets reduced to 10%. So if you're starting with a very high energy gamma ray, it might take centimeters and centimeters of lead shielding to actually block it sufficiently. Alpha rays is the most complex one because it's most easily blocked. So in some sense, it's easiest to work with because it's mostly easily blocked. Oftentimes, you don't even have to shield it. Air around it will naturally shield it for you. So in that sense, alpha rays are easy to work with. In many applications, you don't have to worry about shielding. Layers of dead skin cells will stop the alpha rays. Now, the particular danger with alpha rays is because they interact with the surrounding material so easily. If somehow you accidentally get it inside you, the alpha ray sources inside you, it's even more dangerous than beta and gamma rays. Because with the beta and gamma rays, these rays have some chance of escaping your body without hurting you. But with alpha rays, everything that comes from within your body is guaranteed to interact with something inside your body, ionizing it, causing DNA errors that lead to cancer. So when people do the exposure dose calculation, there's a factor that applies to just alpha rays. With the alpha ray doses, there's a factor of 10 that applies to it just because that once you are exposed to alpha ray, the chance of interaction with the alpha ray and your body is so much greater than with these two. So I guess I kind of talked about these radiations a little bit. And the talk about those, that's what leads to what I want to get to next, which is a principle that applies in the context of radiation safety. And the version I learned is this. I think there's other ones that float around. The version I learned is called ALARA. And it's an acronym for this phrase: as low as reasonably achievable. As low as reasonably achievable in reference to dosage or dose of exposure. There's a saying, dose makes the poison. I think it's saying in medicine. It's a particularly applicable saying in radiation safety. The truth is you are exposed to radiation all the time. As you are watching this video, you are exposed to radiation right now. We are all exposed to a background source of radiation. Some of that is coming from radioactive elements in the soil. There's some average amount throughout the earth, and some sites tend to be more contaminated. Whatever the case might be, you're going to be exposed to some amount of radiation. There's sources of radiation in the food you eat. Banana contains potassium, and certain fraction of naturally occurring potassium is radioactive. So you are eating radioactive potassium whenever you're eating banana. And cosmic rays that I referred to earlier, it's coming from sky. I think even on the sea level, you are exposed to some cosmic rays. And whenever you are flying in an airliner, you are closer to the source of cosmic rays, so you're getting exposed to more cosmic rays. So you are constantly exposed to radiation. So it's not as though you can just be away from all radiation all the time. That's just not going to happen. So our starting place is that the background level of radiation, it's something that's reasonable. That's something that we have survived with for many, many years, millions of years. So even though some of those are probably eventually causing cancer, it's the rate of cancer that we are used to. So as our occupation exposes to more radiation sources, cosmic rays are actual source of concern for airline pilots and flight attendants and astronauts. The number that we are comparing to is the background radiation level. I think I was looking this up just before class session. Think for human adult, the typical amount is something, let me look it up again. Background radiation exposure. It's usually measured in something called RAM, radiation equivalent man. I think this is about right. So the typical background radiation, I guess it says about 300 millirem. That's the annual amount of exposure living in US. So if a source of radiation that you are thinking about, whether it be cosmic rays for airline pilot or a physics researcher who's working with radioactive source, if you do an estimate for, okay, how much additional radiation you are exposed to, and then let's say your calculation comes down to, let's say 3 millirem per year, then you would say, oh, that's way less than background, so you wouldn't really worry about it too much. And that's the two sides of this as low as reasonably achievable. So the reasonable part. So if the expected radiation exposure is already low, then you don't take extraordinary measures to prevent it further, because that would be unreasonable. At the same time, let's say you do the estimate and the estimate comes out to be 300 millirem. Then you don't say, oh, that's the same as background, let's ignore it. You don't do that. The principle is as low as reasonably achievable. So if there are reasonable precautions that you can take to reduce the level of radiation exposure, then you take it. It's a trade-off between how much more complexity does it cost to your work setting. That's the kind of the cost in implementing those. And the benefit would be you are reducing your radiation exposure. And once you are at the level of background level exposure, then going somewhat below that is probably a good idea if that can be reasonably done. So in implementing those measures, the three levers or three things that we typically do in radiation safety is called time, distance, and shielding. I think that was one of the homework questions. And this is ordered in the order of importance. Time is actually the biggest one. It's kind of evident in this background radiation exposure coming as a timed number, as annual radiation exposure. So as an example of when I was doing physics research work that involved radiation source, then I would do the estimate on time, estimating, 8-hour workday. So whatever level of exposure I was calculating from the location of the radioactive source to where my desk was, I would estimate that, okay, I'm gonna be at my desk 8 hours a day and 5 days a week over a period of a year. How much exposure am I getting? Now, I'm not at my desk all the time. My desk is where I spend most of my time, but there will be times when I work with the radioactive source. So I would be within a few centimeters of the radioactive source, and that time would get treated differently. I would estimate, it would depend on the project. I would say, okay, on average, I might be spending 15 minutes per day with this source in very close proximity. And in working out those plans and standard operating procedure, you would limit exposure, because that's the simplest and most effective way to limit your danger to any radiation source, limit exposure to source. And in fact, if you've ever taken X-rays where you're aware, like dental X-rays, you might have noticed that as they are pressing the X-ray button, you might see them step out of the room. It's because the X-ray machine it's a radiation producing machine. It only produces the radiation while it's on. And for you as patient, you get X-rayed only a few times a year. So all those are taken into account. Your doctors figure this is a reasonable amount. You are not at much elevated risk of getting cancer. You are fine. But the technician, that's their job day in and day out. They are pressing the button several times a day. So unless they take extraordinary measures, like stepping out of the room, making sure they're nowhere near the X-ray radiation, over the period of their work, they could be accumulating a lot of exposure to that ionizing radiation. So a lot of workplace safety rules regarding radiation. This is the very first line of defense. You limit exposure to source. If you don't need it to be near the source, then you are not, and you arrange the workplace so that can happen. And that brings us to distance. And I keep talking about being near the source. It's because radiation decreases with the distance. All these sources, at a minimum, follows inverse square law, as in their intensity decreases as an inverse reciprocal of a square of the distance. So, gamma ray, I was talking about how it takes centimeters and centimeters of lead shielding to reduce it by, it takes at least a centimeter of lead to reduce it by a factor of 10. One way you can easily get a factor of 10 reduction of gamma ray exposure, you increase your distance to the gamma ray source by a factor of 3. 3 squared, 9, that's about 10. And so your exposure to gamma ray source reduces by a factor of 3 by just increasing the distance by a factor of 3. So this distance is in the design part of the workplace or research or whatever arrangement. You try to put the sources so that they are as far away from you as you can. If you don't need to directly handle the source, then you don't. Now, if you somehow need to handle it directly, then you use an instrument to not directly touch the source, but be at some distance so that you get as much distance as you can. And shielding is really the last and the final measure. It's something that's meant to come into play when it's not practical to limit time or distance to the extent you can. And shielding is also used in storage because that's where sometimes people can accidentally expose themselves to radiation without knowing that they are. So shielding is really the last measure. And especially with something like gamma rays, which is where shielding is most needed, is sometimes the shielding actually limits your dexterity. It limits how quickly you can move. It limits how much time it takes to certain task with the source. So sometimes trying to get more shielding in place kind of conflicts with limiting the time. So people who work with the gamma ray sources, they often are not wearing heavy leaded gloves because it's much more effective for them to have glove-free hand or wear light gloves and work with the source quickly and be as far away from that as they can be quickly. So shielding is the last measure. It's done either as a fail-safe in case some tourists come around who don't know that there's a radioactive source around, and to safeguard the people who don't know better, that's one, and to in the circumstances where time and distance alone are not enough. So yeah, that's the radiation safety. And since I'm on the video here and I'm in my office, I thought I would actually show you this. So because, again, dose makes the poison, and oh wow, is this not opened? I thought I opened it. So there are places that will sell you radioactive sources. These are what's called exempt quantity sources. I get these for a lab that we do in Physics 4C called cloud chamber, where we are detecting radiation within the cloud chamber. And this company sells it to me without me having to go through a lot of bureaucratic stuff because this is exempt quantity. These sources are so weak. They are of small enough activity that when you do the estimate of, okay, how much exposure would a person get, they will turn out to be very small amount. So that's how they establish what quantity is considered exempt. So let me just pull out one of them. Some of these other sources are for other things. So this is exempt quantity cobalt, cesium, cobalt and cesium sources. And because these are very low amount of radioactive material, I feel completely fine handling it without any other special instruments. And these are also sealed sources, meaning there's a very little chance of me accidentally swallowing the radioactive material in it. Now, having said that, even though it's a exempt quantity, and it's not gonna cause me any harm, even if I hold it in my hand like this. I'm not gonna walk around holding this in my pocket like this. Like that would be stupid thing to do. Again, the principle is as low as reasonably achievable. It's unreasonable for me to walk around with this in my pocket. Like I have no reason to do that. It's reasonable for me to store this far away in a cabinet where I'm not near. Because again, the thing with the radiation safety is it's not a racing game of can you reach the background radiation level. It's whatever precautions you can take reasonably, you take it. But you do recognize that there are circumstances where you have to balance between precautions that can be taken and precautions that are unreasonable to take. And when you are at that balance, you are at what they call ALARA. You've reduced your radiation exposure to as low a degree as can be reasonably achieved. So this is the radiation source. So in the context of physics of force lab, our ALARA procedure is that I only bring out this source when we are doing cloud chamber lab. I don't leave this lying around. It's locked in a cabinet. I only bring it out once a semester when we have these labs, and usually these sources, I'm the one handling it directly. The sources that most students are handling directly is actually this source. And this is it's a polonium source, and it's actually specifically designed to be held in such a way that the radioactive source is at the tip here. And so the way students are usually handling it, it's naturally already a few centimeters away from that. It's also an alpha source, so the air between the tip and their finger will actually show them. So the most dangerous thing that they can do is you poke their skin with it, and it's a dull needle. So yeah, that's a kind of radiation thing. Yeah. So I see a question about outpatient X-ray labs where lead line the half wall that the technicians are step behind. That could be sufficient. It's a question of how thick that lead is. So they have a kind of lead blanket that they put over you, and those are not very thick. That's definitely less than a centimeter because lead is heavy. So that shields you to a degree. And the point is that the level of shielding that something like that personal protective equipment provides, it's very minimal. So for the patients, it's reasonable to provide it, so they do it. And for patients, it's enough. But for technicians, even if they were wearing that lead apron, it would not protect them sufficiently. That's why they either step out of the room where they are far enough away from radiation producing source, or they are in a specifically designated area of the room where someone has looked at it in detail and made sure with all the shielding in the wall or whatever that where they are standing, their exposure to radiation over the number of hours that they're expected to be exposed will be reasonable.
How many here know what isotopes are? Some of you. You've heard the word, so let's just make sure to cover the ground on everything. So in chapter 8, we weren't really concerned with atomic nucleus. We are just dealing with the electrons around the atomic nucleus. The nucleus is whatever it is. Now we are not worried about the electrons at all. Instead, we are concerned with, well, what's at the core of the atomic nucleus. And this is, I don't know what it's supposed to be. Why did they have to draw so many? So, all right, let me count protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Assuming there aren't any that's not visible, that must be oxygen and I can't. Neon. This must be neon nucleus, maybe. So you guys already know about protons, right? From hydrogen atom. Proton was the thing that's at the core of the hydrogen atom. So we can start listing properties of proton and neutron separately. So properties of proton would be that it has charge. The charge of proton is plus 1e, the elementary charge or the same magnitude of charge as electron. because that's how hydrogen atom is electrically neutral. And the mass of the proton from the mass of the hydrogen atom is approximately, mass of the proton is approximately 1,000 GeV per c squared. That's the unit I have it memorized. 1,000 GeV, that's not right. It's about 1 GeV or 1,000 MeV. So let me just write it as 1 GeV per c squared. That's the mass of the proton. All right, so that's proton. You know it exists because that's at the core of the hydrogen atom. What do we need a neutron for? Like, why would people, well, let me tell you one of the properties of neutron. You can kind of guess it from the name itself, neutron. So one of the properties of neutron is that it has charge of 0. Like, why would you even, why are you introducing something that has 0 electrical charge? So it must be interacting with nothing. Like, why are you even bringing it up? Hint for that is in the periodic table. Do people know the history of how periodic table was initially constructed? How was it initially constructed?
By chemical property of elements.
Not by chemical property. I mean, chemical property plays a role, but someone had an idea to order the elements by one particular property. What was that one particular property? Well, they didn't know how to count the number of protons. They didn't even know about protons. Weight, atomic weight. Yeah, they had ways of determining atomic weight. So they listed it by, I think it's probably this one that'll work. So they did it by atomic weight. And once they started listing it by atomic weight, that's when they noticed the periodicity. So hydrogen kind of, well, it defines the baseline. So hydrogen has atomic weight close to 1. It's not exactly 1 because carbon-12 becomes the standard. You guys know that, right? Okay. Now, here's a funny thing. When you go to the next element, helium, your atomic weight doesn't go up to 2. It goes up to 4. So if you're counting number of protons, you went from 1 to 2 protons. Why isn't the atomic weight 2? Why is it 4? So that's where people start thinking, okay, there must be something that's not quite like a proton, but maybe weighs similar to proton. So let's just say mass of the neutron is also approximately 1 GeV over c squared. So what you're guessing is that with the helium, well, it must have 2 neutrons in it in addition to 2 protons. And let's keep going. Oh, wait, I don't want to scroll down that far. Okay, kind of jumps around. So when you look at, you can't really read it. With the lithium, 6.9, so about close to 7. So on average, lithium must have 3 protons and 4 neutrons. All right, my neutron numbers are increasing. Same thing with the beryllium, about 4 protons and 5 neutrons. And let's just keep going and see what happens. I want to just get up to carbon at least. So boron, 5 neutrons, 5 protons, 5 or 6 neutrons. Carbon, is carbon-13 also stable?
Yes.
Okay. So carbon-12 is where atomic mass unit is set. The definition of atomic mass unit is set so that carbon-12 is exactly 12 in atomic mass unit. But when you look at the average, there's enough carbon-13 out there in the world. That average comes up to 12.0. So carbon has 6 protons and 6 neutrons. Are you beginning to notice a pattern? Kind of equal number of protons and neutrons, right? But it's not an absolute law. It's kind of we are at an odd place. But so what we know or are guessing at now is that in the nucleus of the atom, you have 2 different types of particles. Because otherwise, there's no explaining the pattern of the atomic weights you see. There must be a particle that has charge, and there must be a particle that has no charge. And the kind of pattern you see makes most sense if you assume that these two methods are very similar. And this is where the idea of isotope comes from. So the number of protons determines what element you are dealing with. So for example, helium has two different isotopes. I don't know if this is all that helpful. Yeah, it's not all that helpful. I'm just gonna write. So helium has, there are two stable isotopes of helium. So let me use that to introduce some of the notation that I'm going to start using. This is kind of where we start. Isotopes of element. So you guys have some sense of what iso in a word means, right? Or iso, or isos. Like what? Equal, isosceles. So when you start something with iso, it means something is equal. And what's equal? Oh, actually, I don't know what TOPS stands for. I don't think it stands for weight. Because I don't think, all right, I'm just going to leave it there. So it has equal number of nucleons. It has, when you're referring to an isotope of a particular element, you are looking at the particles which have the same number of protons and neutrons. This is what I mean. So elements are things like hydrogen and helium. So hydrogen is an element, and helium is another element. And what makes them distinct elements is their distinct values of Z. So with the hydrogen, Z is equal to 1. And what this really is the number of protons. And with the helium, Z is equal to 2. And this determines all the chemistry that occurs with these elements. Hydrogen having 1 proton in the center, that gives a particular energy levels for the electron that's around it, and that makes certain kind of chemical reactions happen, certain kinds not. Same thing with the helium, with the 2 protons in the center. To make it electrically neutral, you need the 2 electrons around it. They fit into particular orbitals that produces certain kind of energy levels. That's what determines all the chemistry that you see. So these are the chemical elements. But it turns out there's more than one type of particle that has 1 proton in it. So those are isotopes. And the way I prefer to mark isotopes is this simple notation, because you can type it. They are, you list them this way. The name or symbol for the element, hydrogen, and you follow it with its isotope weight. So hydrogen 1 would be hydrogen, something you already know. And hydrogen has 1 more stable isotope that's not as common as hydrogen 1. It's a hydrogen 2, or it has its own name because it's simple enough to have its own name, deuterium. Anyone here have heard of heavy water? Like what makes heavy water heavy? Yeah, it has deuterium in place of hydrogen. So that's why it's heavier. It has more neutrons. And hydrogen has 1 more unstable but long-lived, like 13-year half-life of isotope. That's the tritium, or hydrogen 3. So these are the isotopes of a hydrogen. And the 2 stable isotopes of a helium would be these. So you have helium, I'll go in the same order. Helium 3 is much less common. It's very rare, but you have helium 3, and you have helium 4. That's the most common version of helium. That's why the atomic weight you saw was mostly 4. There's not much 3 in there. And I don't think helium 5 is stable. So that's what, when we talk about isotopes, that's what this refers to. So when you look at one element, the helium, it has, so both the helium 3 and helium 4 chemically, they are near identical. Any kind of reaction helium-4 undergoes, which is not many. It's one of the noble gas elements. So helium-3 is also a noble gas. Any kind of reaction you can have with, that's how you have heavy water. Because hydrogen forms bonds with oxygen, 2 hydrogens to 1 oxygen forms water. You do the same reaction with the deuterium, you get heavy water. So these different isotopes, they don't affect any of the chemical reactions most of the time, but they will affect the nuclear reaction. So for example, this tritium, it can decay into helium-3 in a, well, I guess we were just talking about it, in a beta decay. But it wouldn't decay into helium-4 for reasons we'll go over in a little bit. Okay. So there's one kind of good fact for you to know. So you guys notice the pattern of the atomic weight, right? As you are going higher up in the number of protons, you are seeing that the kind of number of neutrons was increasing to catch up. But it's not really a hard and fast rule, because with hydrogen, this is stable, and that's the most common isotope of hydrogen. So obviously it doesn't need a neutron. And when you look at, well, I guess helium-4 actually does fit that pattern, 2 protons and 2 neutrons. But then you look at lithium, which has 3 protons and 4 neutrons, so what gives? So you don't have any clear pattern or like clear hard rule you can apply. So somebody just plotted all of them. This is a sort of a plot of stable atomic nuclei. So you can kind of see the pattern. So especially at the lower end, you see that the number of neutrons is often equal to the number of protons. If you have 10 elements with 10 protons, I guess that's neon, then you are kind of likely to have a stable isotope with 10 neutrons. So let's double check. What's the atomic weight of neon? So when you look at neon, yeah, atomic weight of neon is about 20. So 10 protons, 10 neutrons, approximately. Now, as you start to go into higher and higher Z value, or higher number of protons and neutrons, it starts to now skew in favor of neutrons. So when you get to very heavy, so uranium-238, I guess it's around the G value of 80, 90 or so, then for stability, you need, well, uranium is not stable. So you need more neutrons than protons to keep it stable for some reason. And you can kind of see it as an illustration here. Let's look at lead. Lead, G value of 82. It has 82 protons. Atomic weight, average of 207, or on average it has 125 neutrons. So that one-to-one pattern starts to break up, and that's what you see here. And I guess intuitively, this is how you would understand it. So, oh, yeah, this is the more, I probably should have led with this. This is a more beautiful diagram. So this is the figure that kind of gives you an intuitive sense. So one thing I have to tell you is that when you look at the atomic nucleus, something should tell you right away that this involves forces that you haven't seen yet. Because what fundamental forces have you seen so far? Electricity and magnetism. And you also seen gravity, but it's so weak compared to electricity and magnetism, it's not worth mentioning. So when you look at this, based on electricity alone, it shouldn't hold together. Because all these protons are positively charged, they should repel each other. And neutrons don't do anything. But somehow, they are being held together. So what people assumed was there must be another kind of unknown force, a nuclear force that's binding them together. And the easy assumption to make is that neutron is actually very similar to proton. Their masses are similar, their spin is exactly the same. The only difference is their charge. But you know, charge is electromagnetic. Maybe it doesn't matter to nuclear force. So you would assume that there's a second unknown kind of force between these particles. Let's just say they are attractive. So whenever you have a neutron, that's contributing to that attractive force. And two protons would also attract each other too, except there's an electrostatic repulsion, so the balance of it is that two protons would repel each other. That's why there's no stable version of helium-2. With no neutron, there's not enough attractive nuclear force to hold it together. And with that kind of intuitive, rudimentary model, what you would guess is, well, the most place where this balance is held, as in the nucleus is not being crunched too much, or it's not, there's enough attractive force to keep it together, is usually the balance of where the number of neutron and number of protons are the same, except as you go into higher Z value, the long-range repulsion of the electric force becomes more important, so you have to kind of keep piling on more neutrons to keep the whole thing stable. So that's sort of where we want to leave the nuclear forces with. We probably won't go into much more than that. Welcome back. We are changing the order around a little bit. I want you to start out with this. So we are back in section 10.4 of your textbook, nuclear reactions. So we'll do the detailed calculation later. But what I wanted to do was kind of set the stage so that we can note how special the thing that we are going to call fission is compared to other common, everyday nuclear reactions. So these nuclear reactions, radioactivity that results in these, I erased them all, alpha, beta, gamma particles, gamma rays, they usually happen in a decay process. So the process that produces alpha ray is called alpha decay. Process that produces beta ray is called beta decay. So I have a couple examples of the alpha source that I happen to know. Americium, I think 241 is right. Let me just double check. Americium 241. If I guessed it right, then it'll be talking about smoke detector somewhere. I don't know. Isotope, radioactive, most common. Where?
The last sentence in that one.
Smoke detector, yeah, okay, 241. So you know americium 241 undergoes alpha decay, and that's used in smoke detector. So the first question you could ask is, well, what does it decay into? Because we still hold to the conservation principles of, well, I don't know if I want to say conservation of mass, but there's something being conserved there. We don't want to just say, you know, I had americium 241, it all goes to alpha particle and then it's all gone. That's not how it happens. So I guess this is how you can look at it. I think I can tell you this. There's a conservation law of nucleons. Nucleon, meaning this is the word used to refer to either proton or neutron. So if you want to talk about particle that's at the atomic nucleus, but you don't want to be specific about is it proton or neutron, you call it nucleon. It's the particle in the nucleus. So we can still hold to the idea of conservation of nucleon. So americium 241, what I do know is that number of proton plus number of neutron is 241, right? Now, in the alpha decay, I think I need to tell you this. The number of protons or number of neutrons, they don't change. In an alpha decay, all that happens is these just get rearranged. So that means in an americium 241 alpha decay, well, you know one thing, you know it emits an alpha particle, right? So it emits an alpha particle. I'm going to call it by its proper name. What it really is, it's a helium-4 nucleus. So this is going to carry away 2 protons and 2 neutrons away. Good? So whatever is remaining here, I kind of know its weight. 241 minus 4, so 237 of something. This is where I have to refer to the periodic table because I don't, but this is going to be my common excuse. I'm not a chemist, so I don't know where the elements are necessarily. I can kind of find them. Okay, here's the americium. Okay, I think it decays into neptunium. That's americium. Take away 2 protons, you get neptunium. So what americium decays into is neptunium-237. So this is an example of alpha decay. And you can do the same thing with the processes that produce beta rays. So the kind of one easy beta source that I know of is tritium. So you can do the same thing here. The tritium, oh, wait, let me finish here. So number of proton here is, oh, wait, I can just copy from there, right? 94. And number of neutrons here is 143. Right? And so when you, so americium, yeah, 96 and 145. Yeah. So with the beta decay, what the one interesting thing that's going to happen is that the total number of nucleons won't change, but the total number of protons or neutron alone will change. So when you look at this, so this says 1 proton and 2 neutrons for a total of 3. And it decays in a way that it turns into helium-3. So it now has 2 protons and 1 neutron. So, okay, so the total number of nucleons is same. And it emitted 1 electron. So there's going to be one more quantity that we want to say is conserved. Anyone see that? Or let me put it another way. I kind of told you that tritium decays into helium-3. What if I didn't tell you? I only told you whatever beta decay process is, it emits an electron, and that's all you knew. How would you be able to guess what this daughter nucleus is, daughter isotope is? Like what principle could you maybe use?
Even what a beta particle is, an electron.
Okay.
You also leave 2 electrons.
Not quite.
Like conservation of charge.
It's the charge that you're looking at. And I kind of see where Kevin was thinking of something that has 2 electrons because you start out with something neutral and you want to end with something neutral. So it's the same idea, except because we are dealing with the nuclears, we are kind of ignoring the electron cloud. So we don't want to think in terms of how many electrons does the atom have. We want to think about what change do we need to make to the nucleus so that the overall charge remains the same. So here, the overall charge, Q, is initially +1. So when you add up all the charges here, you want the total charge to also remain +1. So you have Q of -1 from this electron. So this must have charge of +2 so that they add up to 1. So that means it must have 2 protons, which means it can have only 1 neutron if we are conserving number of nucleons. So, so yeah, that's the beta decay example. By the way, why am I not listing gamma decay here? Like, why no gamma rays? What makes one thing, what's one distinct characteristic of gamma ray that's different from alpha or beta ray? Massless, and also no charge. It's a photon. So gamma ray emission usually happens when an excited state of nucleus goes down to a lower or ground state of nucleus. So you are changing the state of nucleus, but you are not changing the composition of nucleus. That's why I'm not listing it there. There's no real gamma decay, and it's not one that we can kind of do it by identifying what kind of isotopes you are dealing with. So all these processes are, I guess, what I need to highlight is that these are all spontaneous processes. They have some half-life, It's determined by property of this and this isotope. And you can maybe calculate it, but it's not something you can really affect. It's a spontaneous emission process. These are all spontaneous processes. They have some half-life. It's determined by property of this and this isotope. And you can maybe calculate it, but it's not something you can really affect. It's a spontaneous emission process. Yeah? Now, what we are going to refer to as a fission is a kind of an activated emission or stimulated emission. So this is a very rough analogy, but you can kind of think of this as incandescent light, kind of emission that happens when something gets hot. And what we call stimulated emission is like the laser light. So that's what happens with the fission. So this is something that just happens in nature. You don't need any special arrangement of devices. It just happens in nature. Stimulated thing, you have to build a device that does that. So to make a fission happen, you have to have a device that kind of you need to design a device to make that happen. So your textbook has a whole section on it. Let me just highlight some portions of it that I want you to be aware of before we look at a simulation that's kind of fun thing to play with. So most naturally occurring isotopes, if you simply leave it out there, they're going to decay by alpha or beta decay. So these are kind of simple reactions, right? You start out with one, it splits into multiple things. Fission reactions, you don't start out with one. You start out with several. You start out with two. So this is an example of fission reaction. We can just look at one of them because kind of what happens on the right-hand side, there's many different possibilities. So what I really want you to pay attention to is the left-hand side, your starting element.
Chain reaction. Okay, this is not the best picture, which is why it's good that I'm gonna do the simulation. What chain reaction describes is you have a first thing that's being excited through injection of a neutron, and that produces additional neutrons that can cause more of these fission reactions. But sorry, this picture doesn't quite do the justice at this idea. So let me go to the PhET simulation, which will help us explore this idea of chain reaction in the context of fission reaction. That's much more exciting than what the diagram shows. Let's see. I think it might be called a fission. Yeah, nuclear fission. They haven't updated this yet. So this is a kind of a quick schematic description of fission. You have a fissile isotope, and by fissile, well, sorry, I'm using fissile a little bit loose. We have an isotope which can be caused to undergo fission. So this is in a state that's a metastable state. And if you are just waiting for this to spontaneously decay on its own, it'll take a long time. Uranium-235 has like millions of years of half-life. But you can speed up this reaction by giving it a little bit of energy. And the form in which you give it a little bit of energy is by striking it with a neutron. So if I fire a neutron at it, that causes this to go to this higher energy level, which then can decay into those split daughter nuclei much more quickly. So that's the description of, in the microscopic, a single nucleus model, how fission happens. So it requires a presence of isotope with the right nuclear properties. And you need a second ingredient, which is the neutron that you strike with that isotope. In chain reaction, so what you have is a combination of those two ingredients in a very particular combination. So, when you have a single isotope, You get a reaction and you're done. Okay, that's a reaction. It's not a chain reaction. Now, in most natural state, the atomic nuclei don't sit by themselves. It's around many other atomic nuclei. Now, well, let's look at that interaction. If you have more than one atomic nuclei nearby, then this is still kind of it's not all that interesting. And for us to get additional reactions, we would have to keep putting in neutrons. So that doesn't seem very it feels like it takes a lot of effort. It doesn't feel like something where you trigger something and something big happens. What happened was something small and it didn't continue happening. So that's not quite chain reaction. For us to get chain reaction, what we need is not just a few atoms. I think right now the way these are arranged, it's probably more likely to get a few more reactions. Okay, that was a little bit more interesting than before. For us to get chain reaction, that's more similar to actual nuclear explosion, nuclear fission bomb, A-bomb explosion, is what happens when you have enough of these fissile isotopes in a confined space, much more densely packed together. So in an arrangement something like this, we'll get a fission reaction. Let me pause the simulation so that I'll have time to talk. So I fire it, and so here's a neutron coming out, and it's going to strike its first uranium-235 isotope. Now, watch what happens. As this splits, it splits off multiple neutrons, 2 or 3 neutrons. And now these are arranged in such a way that the neutrons that come out, they have a pretty good chance of hitting another uranium-235 nucleus. Or in other words, this collection of uranium-235 has critical mass. So these neutrons that are coming out, they are each going to hit another uranium-235 and cause more neutrons to come out, and more neutrons to come out, and so on. And as that happens, because now there's basically a flood of neutrons, and this is what chain reaction describes. It starts out with one small trigger, and each step in the reaction, it produces more of what's needed to keep the reaction going. And the arrangement you need to keep the chain reaction going is for a critical mass of fissile nuclei to be collected together in the same place. And there's a lot of kind of social analogies that you can draw. Sometimes you talk about critical mass of activists and whatnot. But, well, this is the physical description of when you have critical mass of something that can create a nuclear bomb. Now, in nature, you don't see nuclear bombs just forming spontaneously. Even though normally when you find atomic nuclei, you will see them collected in, they're not existing a single atom. They exist in a solid packed with many other nuclei. So why don't we have nuclear bombs going off all the time? The reason for that has to do with the purity. That's not the quite. Well, we do talk about refining. It has to do with the isotope composition of uranium. The natural isotope composition of uranium is more like for every one uranium-230, I can't get one. For every one uranium-235, there's 100 uranium-238. And uranium-235 and uranium-238 have different properties with this key difference. With uranium-238, when you strike it with a neutron, it becomes uranium-239. And uranium-239 does not undergo fission. It will later on undergo beta decay to become plutonium-239, but it doesn't undergo fission. So uranium-238 is it's a neutron absorber. Neutron strikes it and it's gone. So when you have an arrangement with a bunch of uranium-235. So, you know, this is the setup that produced that chain reaction and nuclear explosion. You can mess up this arrangement by introducing uranium-238. Let me just put equal number of uranium-238 as, all right. Sorry, I guess there's some limit to how many atomic nuclei I can put here. Something like this. Okay, let me first make sure that it's still an arrangement that will produce chain reaction and what kind of looks like an explosion, you know. 70 uranium-235, that's enough. All right. So now let me just say it's a half and half, uranium-235 and uranium-238. This is actually more highly enrichment. That's what I was looking for. The process is called enrichment. It's more highly enriched than naturally occurring uranium because it's a 50% uranium-235. And watch what happens. Oh, wait. Oh. Yeah. So, you know, the neutron strikes on uranium-235, and there's one kind of explosion, and then there's a, oh, wait, okay, I guess. So, I guess, yeah. But let me just, okay, so here, now the next one I fire is going to hit uranium-235, but you will see its impact limited because so many of those neutrons are being absorbed by uranium-238. So, well, it's I guess right on the border. So you still have uranium-235 that wasn't reached. So that was a 50%. Let me go down a little bit more. Let's say about 30%. That's about 30%. And let me just double check that if in the absence of uranium-238, that's still enough uranium-235 to cause chain reaction. They are densely packed enough. There is a critical mass. But with the presence of uranium-238, I have to fire a couple times. It's now a couple times. It's now no longer enough. The neutrons keep getting absorbed by uranium-238, and you don't have a sustaining chain reaction. What used to be a critical mass of uranium-235 is now, it's not a critical mass anymore. So when we describe critical mass, it's a combination of how highly enriched the sample is and all that. So there's also, you know, kind of social analogy you can draw, how sometimes other people can be drags. But that aside, this is the reason. I think somewhere I might say something about how a nuclear reactor cannot cause the same type of explosion as an atomic bomb can. And the biggest reason for that is the how highly refined the uranium fuel that the nuclear power reactor uses. So we talk about weapons grade uranium, and weapons grade uranium is something like a 99% uranium-235. The reactor grade, the nuclear power reactor grade is, I think it's only a few percent. And some of you might remember in the news about Iran enriching uranium for their research reactors. And research reactors might use uranium enriched to the level of 40% or something like that. That's used for, well, physics research. But even at 40% enrichment, it's not high enough to be made into a bomb. To make a nuclear bomb, you need something that's at, I don't know the exact percentage, but 90+% uranium-235. So that's a chain reaction and a description of what can be done to mess up chain reactions.